Now, hopefully, we are ready for the second part. And yeah, this part, I have to say, is kind of boring, probably the most boring part of the course, just to get the definitions, basic definitions out of the way, okay? So I warned you, but let's see. So directed network, usually we denote by G, given by N and A. N is the set of nodes, A is the set of arcs. So typically when we deal with directed networks, we'll use N and use the term nodes for nodes, right? And then A and the word arcs for arcs. And with undirected networks, typically we'll use the notation V and we'll call them vertices, and then E and we'll call them edges. But this terminology is applied both ways. It's not, there is no clear distinction really, so it's just an agreement, and in much of the literature it's like this, but not necessarily. There are different terms that people use. So in this case, the nodes are 1 through 6, and then we have the arcs listed. So as you can see, with directed arcs, we have these pairs in the parentheses represented directed arcs. And in this case, the order in which you list the nodes matters, right? So usually the arc points from the first entry to the second entry. So from 1 to 2, let's say 3 to 2, and so on. If you have an arc ij, we have the node I that is called tail, the node j is called the head, and we call these nodes adjacent to each other. So adjacency is the relationship between the nodes, okay? And then we say that ij emanates from node I and terminates at node j. Then the arc is incident to both nodes I and j. So incidence is the relation between the arc and the node. Then it is an outgoing arc for node I and incoming arc for node j. So, and again, you know, this is something that is pretty much common sense. And if I told you this, if I use this terminology even without showing you this slide, you would probably understand what I'm talking about. As we said, the vertices forming an edge are called adjacent or neighbors. And then the set of vertices adjacent to V is called the neighborhood of V, and we denote it by NG of V. So here we specify the graph in the index just to make sure that it's clear what graph we are talking about. And the main reason for this is because later on we'll be using subgraphs or induced subgraphs, and sometimes we'll consider the neighborhood in the induced subgraphs, in which case G will be replaced with whatever denotes the subgraph. The in degree of a node is the number of incoming arcs, right? So the out degree is the number of outgoing arcs. The degree is the sum of in degree and out degree combined. Most of the time, actually, in this course, we'll deal with undirected graphs. The concepts that we'll study, many of them can be extended to directed networks, and this could be actually maybe a project that somebody will pick. But the basic methodology is developed for undirected graphs, and in undirected graphs we don't have the directions, which means that you can think of this as having directions both ways, really, right? So let's say if you have a road network where you can, it's not like a one-way road, but both ways, and typically we just represent it with an undirected arc, but depending on the situation, sometimes for some problems, depending on what problem you are solving, you represent it with two arcs pointing in different directions. In undirected graph, as I said, we denote the set of nodes of vertices by V, and we use the term vertices, and the pairwise relations are described by edges and is denoted by E. So in this case, again, you have 6 vertices, and then the edges in this case are represented by sets of 2 vertices. So in this case, there is no direction. It doesn't matter if it is 1, 2 or 2, 1. This notation is just for the set, right? So a pair of vertices. The order doesn't matter. Then you could have multiple arcs or loops that loop. A loop would be an arc from a vertex to itself. But most of the time we'll deal with simple graphs, unless otherwise stated. We'll deal with the simple graph. A simple graph that is a graph that has no loops or multi-arcs. We call G prime with the set of nodes N prime and the set of arcs A prime a subgraph of G if the set of nodes is a subset of the set of nodes of the original graph, And then the set of arcs of the subgraph is a subset of the arcs of the original graph as well. Let's say if I have G given by this graph right here, then n prime will be the subset of vertices for which I'm looking at the subgraph 1, 2, 3, 5. And the set of arcs is given by 1, 2, 2, 3, 3, 5, then my subgraph is going to look like this, right? I just specify the arcs that are listed here and the nodes that are listed here in n prime and a prime, right? If I look at these nodes 1, 2, 3, 5, there are other connections between these nodes like 1, 3, for example, and 1, 5 that we ignore when we form this subgraph. So, and the definition of subgraph allows that. But then later we'll talk about induced subgraph. That will be different. Induced subgraph is completely determined by the set of vertices that you take. Once you specify the set of vertices, the subset like 1, 2, 3, 5, like we did in the previous example, all the arcs between these vertices in the subset must be included in the subgraph. And obviously others that are not between these vertices cannot be included. The key message here is that the subset of vertices determines the subgraph. You don't need to specify the set of arcs because all the arcs between these vertices in the subset must be included. And this is what you have here. So you have to include 1, 5 and 1, 3. The spanning subgraph would be a subgraph that spans all vertices. So something like this. Here you have a subgraph that spans all vertices, so includes all vertices in the graph, so we call it a spanning subgraph. Then walks. So what is a walk? Let me just illustrate a walk by this example here. So it's essentially a sequence of nodes and arcs through which you kind of walk the graph, right? So let's say we start at node 1, then we go through arc 1, 2 to node 2. So now node 2 is included in the walk, and see the way we specify it is the sequence of both nodes and arcs. So from 2 we go to 5. So as you see, we don't have to respect the direction. So you can go against the direction with the walk. So in this case, we go from 2 to 5 against the direction. So the arc that we include in the walk is still 5, 2, but we get it the wrong way, right? So it's like you're going against the allowed traffic, but you get to node 5. Node 5 is included, then 5, 4, 4 is included, 4, 2, then 2, 3, 3, 5, 5, 6, then from 6 to 4 against the traffic, and then the alternative way of representing the walk, you don't have to list all the nodes and arcs. Just by listing the nodes or just listing the arcs would do it. So in this case, we are just using the nodes. This is a more typical way of representing the walk. Then there were like a couple of other definitions there. A directed walk is a walk such that for any 2 consecutive nodes, you walk along the correct direction, essentially. So the directed walk, you have to respect the directions, okay? And general walk, you don't have to. We kind of talked about the Eulerian walk, right? So when you visit all the arcs in the network exactly once, so that was the definition of the Eulerian walk. There is a concept of a path as well. So what's the difference between a path and a walk? A path is a walk without any repetition of nodes. So you cannot revisit the nodes in the path. So and then an arc ij in the path is a forward arc if you essentially move along the correct direction. And it's going to be a backward arc if you're moving against the direction of the node. So and then a directed path, just like a directed walk, would be a directed walk without any repetition of nodes. So yeah, you respect all the directions. Different than walk, you cannot have repeated nodes anymore. Then a cycle is a path that starts and ends in the same node, right? So you don't have internally revisited nodes, but the first node is also the last node in your walk, and you have no repetition, so that's a cycle or a path. Now, if you have a spanning cycle or a spanning path that goes through all the nodes, we call this Hamiltonian cycle. An optimization version of this problem, if you're looking for a Hamiltonian cycle of minimum length And then this is called the traveling salesman problem. It's a really, really tough problem. So then a directed cycle is just like with a directed path, right? So you just follow, you respect all the directions as defined. You call a graph acyclic if it contains no directed cycle. And the length of a path, we already talked about the length of a path, right? But we haven't defined it yet. It's the number of edges that the path passes. You just count the edges, right? So this is in terms of the graph theoretic distance, but then you can also have the weights or the distances associated with every arc. So then it will be the sum of weights, right? So like in the traveling salesman problem, the length of the cycle will be the total sum of the distances of individual arcs. So essentially the sum of arc weights defines the length of the path, right? But if it is unweighted graph, then you kind of think of every arc as having a weight of 1, and you just count the arcs that are included. So, and then the graph is connected if there is a path between any pair of nodes. If it is not connected, then we have what we call the components, or the connected components of the graph, so that you can decompose the graph into connected components. So essentially, I think it's kind of obvious how the disconnected graph will look like, right? So essentially we'll have parts that don't have arcs between them, and then the connected parts correspond to the parts of the graph that have a path, any two vertices have a path between them within the component, right? So then we call a connected graph strongly connected. So this is for directed case. If there are directed paths between any pair of nodes in the graph. So let's say you have a path from I to J, which is directed, and then you have a path from J to I, which is also directed. So then you call it strongly connected. And then the distance between two connected vertices is the length of the shortest path between these vertices in G, naturally, right? So yeah, in the directed graph, you have a path, at least one path between any pair of nodes, and then to determine the distance between the nodes, you find the shortest path, right? What's the diameter of the graph? This is the longest distance between a pair of vertices in G. So you look at the distance between any two nodes, right? Pick the highest one, and this will be your diameter of the graph. A cut, so this is the edge cut actually, is a partition of the set of nodes into two parts, S and S bar. S bar would be whatever nodes you don't include in S. So essentially you split your nodes into two parts, right? So all the edges in between will be the edges that are included in this cut. Given two nodes S and T, an ST cut would be a cut that has S on one side and T on the other side, right? A tree is a connected graph with no cycles. So if you draw it, it looks like a tree. A forest is a collection of a tree, so meaning that every connected component is a tree, so it has no cycles. Next concept we'll talk about is the complement graph. The complement graph is essentially something that complements this graph to make it a complete graph. And by the way, a complete graph would be a graph that has all possible edges. So here, let's say if I added a couple of arcs between 2, 4 and between 2 and 5, then we would have all possible arcs in this graph, which means that this is your complement graph here. So just these two edges. So essentially, to obtain the complement graph, you add all the edges that are missing here and remove all the edges that were there before. Both combined will give you a complete graph, right? So they complement each other. Now we can use different structures to represent the graph, right? Node arc incidence matrix is one way to do it. And let's see how it looks like. So here you have essentially a matrix which consists of zeros, ones, and negative ones, right? So you have the rows that correspond to vertices and the columns corresponding to arcs. So and this is a node arc incidence matrix. So nodes in the rows, arcs in the columns. For each edge, you essentially represent it by putting 1 in the row that corresponds to the first node in this arc, and -1 in the row that corresponds to the second entry in this arc, right? So let's say if I pick an arbitrary column here, so let's say this one. So I have 1 in the third row, -1 in the second row. So we have an arc from 3 to 2 here, right? So from positive to negative. So this is one way to represent a graph. And the representation of a graph, of course, the data structures that you're using is important for the analysis of the algorithm. Depending on the algorithm, one structure, one data structure may be preferred over the other. For example, this data structure that we are using here, the node to arc incidence matrix, is convenient to model the minimum cost flow problem. So in the minimum cost flow problem, you essentially have a directed network. For every node, you have a node's demand or supply. So essentially, you need to move the goods around the network, right? So this minimum cost network flow problem is a very general model that covers a lot of network problems, such as shortest path, maximum flow, and so on. So it's a central problem in network optimization, which is one of the easy to solve problems, can be solved in polynomial time. You have this B of I, right? So it can be either a supply or a demand node, and I will be a supply node if B of I is positive. So this means that you have a supply of the good, and then we call it a demand node if B of I is less than 0. So essentially there are supplies, there are demands, right? So you need to satisfy the demands by sending the supplies from supply nodes to the demand nodes, right? So you need to do it at the optimal cost. So there are transshipment nodes. Transshipment nodes are the nodes that have no supply or demand. You just pass through these nodes, right? And then for each arc, by Cij, we denote the cost of unit of one flow on this arc. So how much it will cost to transport one unit. Then there is the arc capacity given by Uij. So this is the maximum you can send. So let's say it could be a truck capacity or something, or the train capacity. You cannot send more than this. There may be a lower bound on the arc's flow. That's also a possibility. So for example, in pipelines, you cannot send less than a certain quantity as well, right? So there can be a lower bound on the quantity that you have to move as well. And by n, in this case, n calligraphic, not to confuse with n that we use for the set of nodes, we denote the node arc incidence matrix of G, and then the minimum cost network flow problem can actually be formulated very easily using this data structure as minimization of C transpose times X, subject to Nx is equal to B, and then X is between L and U. So see, you have this flow balance constraints here. So this is the amount that you ship out of node I total. So this is the amount that you receive in node I. And that difference must be given by B of I, right? So this is how you formulate this flow balance constraints. And then you have the capacities of arcs. So you have a lower bound, you have the upper bound, and then you can easily verify that in matrix form, this is exactly what you have. So you multiply this matrix N by the vector X, where vector X is of the same length as you have the number of columns in this matrix. So and then if you do this product here, N times X equals B. So this is exactly the representation of the flow balance constraints. So nice and compact formulation. Node-to-node adjacency matrix is something that we'll use more often for the type of problems that we are considering. You just have an n times n matrix. By small n, we usually denote the number of vertices or the number of nodes in the network. And by small m is a common notation for the number of arcs or edges. This is an n times n matrix, meaning that you have as many rows and columns as you have vertices in the network. And then if you have an arc from I to j, then the ijth entry of this matrix is going to be equal to 1, and it is equal to 0 otherwise. So for example, here for node 1, the out neighbors are 2 and 3, so you have 1 for the second column entry and for the third, and the rest are zeros, right? So, and you represent it this way for every node. Now, if you had an undirected graph, this matrix would be symmetric, right? So for a directed graph, it doesn't have to be symmetric, and it's not in this case. The space that you are using is what? N square, right? The space you are using for this one is N times M, which is generally more space than N square. So then finally, we'll mention also adjacency list, which is another common data structure used to represent networks. It's similar to node to arc incidence, but here you don't have a matrix. You just list the out neighbors for every node, right? So let's say for 1 and 2, so it's a linked list. All the neighbors here linked to each other, and then this is the end of list here. So then let's say for node 2, you only have an arc to node 4, so this is reflected in the second row, and so on, right? For every row, you just list all the out neighbors, so essentially wherever you can travel according to the direction is listed there. The next few concepts that we're gonna mention have to do with this network science. So what is network science? So this is a definition of National Research Council. This is a relatively new field, and I would say sometimes it feels like many of the things that are discussed in the so-called network science is like reinventing the wheel. So there are many things that have been done in graph theory, computer science that people knew about for a long time. And then here comes the network scientists that are typically people with background in physics who discovered graph theory. And they come up with some fancy name for old concepts, and it's all over the media. That's one side of this story. But on the other hand, I think the physicists being attracted to this domain introduced a lot of new ideas also that made better connections of very well-known theory to the real world. Because physicists, they tend to observe real-life phenomena, and they look for mathematical description, and sometimes they're not aware of one that already existed, so they kind of reinvent the wheel, right? So, but at the same time, they introduce some new elements, some angles that mathematicians really didn't think about when they introduced the concept. So there is quite a bit of value to this network science work, and I think it also gave a lot of publicity to networks field in general. So there were many articles published on the topic in popular literature. This attracted more researchers to network science, right? So the definition of the US National Research Council from 2006, when this field started maturing a little bit, network science is the study of network representations of physical, biological, and social phenomena leading to predictive models of these phenomena. So this is essentially what we are interested in when we are applying graphs or these network models to real-life data. This is what we are trying to accomplish. So I think this is a pretty good definition. And I'm going to give you a taste of some of the things that are being studied in this field of network science. They essentially try to capture various interesting properties of networks that you observe in real life, and they try to connect them and use these network properties to explain this natural phenomena. At the early period, of course, there were a lot of papers with empirical studies where people would just analyze particular networks, and then they would just describe, here's what we observe. There were a lot of these papers coming from applications, and then people kind of tried to systematize this a little bit, and then some properties were emerging that seemed to be relatively common between the different networks. And I mentioned some of this when you're looking, let's say, at the market graph, right? What we typically observe is that many of these real-life networks that are very, very large, they tend to be sparse. So they have a low edge density. So let's say, imagine, World Wide Web, right? So this is a huge network. There are millions and millions, if not billions, of web pages. How many hyperlinks do you have from a web page? Maybe a few thousands at most, right? Or, I mean, there are some aggregators that can have a lot more, right? So, but a typical node has a degree that is very low compared to the overall scale of the network. So the network is very, very sparse, right? So then we observe these small world properties. Small world property tells you that the average pairwise distance between the nodes is low. So for example, in World Wide Web, the claim is, and there were like some papers claiming that, oh, the diameter of the web is no more than, or like the average distance is 6 or something like this, you know. Despite the sparseness, so there are very few edges used, right, relatively speaking, but the reachability is very good. So the average distances are low, and the diameter of the network is typically very low compared to the size of the network. And then, you know, there is this cultural thing, 6 degrees of separation you probably heard about from elsewhere, right? So that's essentially the other way of saying that the diameter of the global social network is low, so you are 6 handshakes away essentially from any person in the world, right? So that's the claim of this 6 degrees of separation phenomenon. In this case, degrees is used differently from what degree means in graph theory, right? It's more like distance 6 separation. This is referred to as small world phenomenon in network science literature. So you see the difference in terminology, like graph theory terminology looks kind of boring, right? So here you have like cool stuff like small world, scale free. Scale free would be what I mentioned before with respect to the market graph. So the number of vertices of degree k that we denote by xk is proportional to k to negative gamma. So again, you have this preferential attachment type properties in dynamics, you know, when rich gets richer and you keep observing this phenomenon. So it seems to be pretty stable structural property that you observe in many real-life networks. Surprisingly, when you look at this analysis of various networks with huge sizes coming from different domains, these are the properties that tend to persist in all of them. And then these networks, they tend to be very well clustered. You know, if you think about a totally random graph, so if you just randomly throw the edges in the graph, that graph is a perfect example of a graph that is not clusterable because there are no well-defined clusters. So that's why random graph models are usually not very good for real-life applications. Like if you look at the uniform random graph, some people in the community argue against running any experiments on uniform random graphs because they say, oh, these never arise in practice, so there is no point of running the experiments on uniform random graphs. I wouldn't be so categorical because uniform random graphs, they play their role and they're important. Let's say if you want to learn the scalability of the algorithm, how far you can go, let's say with a particular type of algorithm. So uniform random graphs are actually good to have as a test instance. In some cases, it's justifiable. But generally, if you are claiming that a uniform random graph describes some real life phenomenon, in most cases, this is a big stretch. You know, typically, you observe a much more clustered behavior in real life. This is something that they describe with the observation 2 people are more likely to be friends if they have a friend in common. Connections in real world, so like in social networks, they don't happen randomly, but you're more likely to get to know people with whom you have common friends. And to quantify this level of clusterability, network scientists introduced the clustering coefficient. So this is a relatively recent concept compared to all these old graph theoretic concepts, but it makes a lot of sense. The clustering coefficient is meant to characterize this structural feature of small world networks that the higher is the clustering coefficient, the more clustered or clusterable the network is. And this is how it is defined. All right, so local clustering coefficient and global clustering coefficient. The local clustering coefficient, which we denote by Ci of a node of degree di in G, is given by this expression here. So now let's see carefully what this expression represents here. Ajk's here, so these are the entities of the adjacency matrix. Remember the adjacency matrix, it just had ones whenever you have an edge and 0 otherwise, right? So let's say I have I, and then jk are the neighbors. These are 2 neighbors of I, and we add ajk to the count, right? If there is no edge between j and k, we don't add anything. If there is an edge, then we add 1 to the count. So essentially what it does it just counts the number of edges between the neighbors of the vertex I, right? So it counts the number of neighbors, the number of edges between the neighbors, and then in the denominator we have the maximum possible number of edges in the neighborhood, right? In the neighborhood graph. So what is this? So this is the degree of I, choose 2. So this is the maximum possible number of edges that you can have in this neighborhood, right? So n choose 2 is what? N times n minus 1 over 2. So this is the number of pairs that you can pick from the given set. So this essentially is what? Is a local density of the neighborhood. So you look at the neighborhood and look at the edge density of the neighborhood of a given vertex I. So this is your local clustering coefficient. So see, these are like, you know, again, you know, this kind of tests this idea if two people are more likely to be friends if they have a friend in common, right? So this density kind of measures to which extent this is the case, right? And then for the global clustering coefficient, this is like the averaging of these local clustering coefficients for all the nodes. So here you just sum up this type of sums that you have here in the numerator for all the nodes in the network, right? So for each I, you are going to sum up these terms here from the numerator, and then for the denominator, you're just going to sum up all the di's choose 2, right? So this gives you like the average in a clustering coefficient essentially across the whole network, right? Yeah, so these are the measures of clustering, or you know, clusterability of a network that are being used in the network science. So, and these are some of the common characteristics people use in this emerging field of network science. There are many other cool terms that they're using, like percolation for connectivity and so on. So, but a lot of this is, you know, just a terminology, different terminology for things that have been used in graph theory for a long time. But again, you know, some of these concepts are actually pretty interesting and new. Here is an interesting property of these clustering coefficients, actually. So you would think that if I add edges to the network, the intuition may tell you that probably the clustering coefficient should increase. But the reality is actually different. And when you think about it, it makes a perfect sense, because by introducing some new arcs, so for example, you know, if you have communities that are very well clustered, right? So then you meet somebody from outside your community, and then there is no connections to people that you already know. So this is going to reduce your local clustering coefficient, right? So, and here is a small example illustrating this. So say I had this network here. First consider it without the arc 3, 5. So without it, you had the local clustering coefficient of nodes 3 and 5 was 1. So for nodes 3 and 5, look, 3 and 5 had only 2 friends each, and those friends knew each other, so the clustering coefficient was perfect 1, right? So cannot be higher than that. So, but then you introduce a new friendship here, and all of a sudden now they have many friends, and it's not very well clustered, so the local coefficient for them drops to 1/3, and then the global clustering coefficient of the whole network drops from 6/10 to 6/14. So this is an interesting property to observe.
What are you doing, Josh? I'm writing this down. This is good stuff. Yeah.